This last one, when you look at it at first glance, it doesn't necessarily look like the combined gas law, but let me kind of show you how the combined gas law can work for any gas law problem. A gas has a temperature of 14 degrees Celsius. So here we have temperature 1, and we know that we cannot leave that as Celsius, so we're going to go ahead and do 14 plus 273, and I get 287 Kelvin. It tells us the volume is 4.5 liters, so volume 1 is 4.5 liters. If the temperature is raised to 29 degrees Celsius, so temperature 2, cannot leave it as Celsius, so we're going to add 273 to 29, and we're going to get 302 Kelvin. What is the new volume? Okay, so we look at this and we're like, wait a minute, we know that combined gas law looks like this, but if you read the question, it tells us that the pressure is not changed. So we could make the pressure any number as long as it's the same on both sides. You could say that the pressure is 1, the pressure is 2, it doesn't matter. Regardless, that pressure value completely comes out of the equation. And now what we see is Charles' law. V1 over T1 equals V2 over T2. And so we're going to go ahead and plug in those values. Volume 1, 4.5, divided by 287 equals volume 2, that's what I'm trying to find, divided by 302. And so once again, we would just cross multiply. I'm going to put 4.5 times 302 in my calculator, except I need to put it in correctly. And then I'm going to divide it by 287. And I get that volume 2 equals 4.735, but of course we want to look back at the original number of significant figures, and it looks like that would be 2. So volume 2 is going to equal 4.7 liters under those circumstances. So we can use the combined gas law because we understand that it's actually a combination of Charles, Boyle's, and Gay-Lussac's.